made Sculpties back in the day when Sculpties were the new hot thing. Oh, all right, Damien, right. So, and then if you collect that data, you can keep a historical record. Yeah, I do. I still have more or less the same avatar. I know that I wore this same outfit giving talks back in the Micah days. So I haven't kept up with the all the new trends. I fear I'll get started in a couple minutes here. We'll just give a couple minutes for latecomers to come in. All right. Well, hello everybody. I know I recognize many names here. Of course, I have seen you here before, but there are some names I don't recognize. So, welcome to the Science Circle, and I am Rob Knop. I've been giving talks in Second Life for a long time now, and I think I have listed five. I think I'm on my fifth different job since I've been giving talks in Second Life. I started at Vanderbilt. I don't know how many talks I gave back when I was at Vanderbilt, because then I worked at Linden Lab actually for a couple of years, and then I was at Quest University, and now I am at another place called Westminster College, and that's what you see here. So Westminster College is a small liberal arts college in western Pennsylvania, about an hour north of Pittsburgh. We're very small. We have something like 1,200 students, more or less. Quite a small place. There's three of us in the physics department, and that means that physics majors can get a lot of individual attention. Last semester when I was teaching E&M, there were three guys who spent a substantial fraction of the semester either in my office or just outside my office trying to figure stuff out. But, that's how things go at a tiny school like this. And today I'm going to talk about eclipses for a couple of reasons. One, because we just had a eclipse that went through the middle of the United States, where where is everybody from? How many people here are from the U.S. versus Europe versus somewhere else? But if you're in the United States, you were maybe close to the eclipse, and we were able to see it. Yeah, I see a lot of U.S. people here. The other reason, of course, is that we're doing several things in honor of Padioplasma, Paul Doherty, who just sadly left us. Oh, what was it? A few weeks ago. I don't remember the exact date. It was before the eclipse. But Paul, saw many eclipses over the course of his life. He worked at the Exploratorium, which was this this really awesome science museum in San Francisco. If you're ever out in San Francisco, check it out, the Exploratorium. It's a really neat place. They have all kinds of hands-on exhibits where you just go up and you can play with stuff and figure out how things go. And every time I go there, I see things that I think, oh, I want to take that back and use it in a lab. I was just there last May. I was out in May visiting because I have family in San Francisco. So I was out visiting, and I actually met with Paul at the Exploratorium when I was out there. And at the time, he told me that he was planning on retiring within the year. And at the time, his cancer was still in remission, or at least that was his understanding. So it was all very sudden. It's pretty sad, that I saw him just in May, and then, of course, the cancer came back. Cancer is kind of a monster. But even then, when I was out there, one of the things Paul spent a little time showing me was several of the optics and vision exhibits they have. And I saw a few things there that are just really neat. John 726, I'm actually talking already in voice. So he may need some help. Anyway, some light and vision things about how people see, and you can get two different ways to make something that looks like exactly the same yellow color. Anyway, Paul was really amazing. The amount of energy that he had and the enthusiasm he always showed at all times. My mom actually would go to the Exploratorium for evening events that he would host, but he hosted this in the real world as opposed to Second Life as Padioplasma. So he had an outfit and everything that he would become Padioplasma in real life, as well as Paul Doherty in real life. I'm sorry if I'm a little bit quiet, but the other thing you can do, maybe if you have voices from camera position, you can zoom in on me. Anyway, and so he was doing this series about all the elements in the periodic table, and my mom and her husband would go and see these. Yeah, you should see green waves above my head. Green wiggly. So anyway, so because eclipses are sort of a hot topic, and because it was something that, as part of his job at the Exploratorium, Paul traveled all over the world to see eclipses, I thought I'd talk about them today. In fact, here's a picture from last year. There's Paul on the left. I don't actually know who that is on the right, but if any of you recognize who that is, shout out who it is. And you can see he's doing a little demonstration there with the Earth and the Moon. There's various other people in the back. This is on a small island somewhere in Micronesia where he went to see the 2000 eclipse. Total solar eclipses happen every couple of years or so. There's multiple solar eclipses every year, but there's not always total solar eclipses. But often they just go over the ocean or over some islands. So sometimes they go through highly populated areas like the 2017 one, which was a good deal. But of course, if you want to see lots of eclipses, you have to travel to go various different places, such as this one. Or sometimes you can go on an eclipse tour. I know there used to be, I assume there still are, cruise ships that will take you to eclipses in the ocean. I've never actually been on one of those, and I suspect it costs quite a bit of money because you're on a cruise ship, and that costs a lot of money. But anyway, but this year, yes, he is using a hula hoop for Earth's orbit. Actually, it's the moon's orbit around the Earth there that he's using. And he's got it tilted, and I'll talk about that in a little bit here. So the 2017, how many people saw the 2017 eclipse in totality? I saw the, I did actually go down to the line of totality in order to see it. And it's just, so back in 1991, I think it was, I was in Los Angeles at the time, Pasadena actually. This is back when my second or first year of grad school. I think it was the summer after my first year of grad school. There was a total eclipse that was down in Mexico. I don't think it crossed through the U.S. at all. It got to 80% or something like that in Los Angeles. And so I was out, and we had some telescopes with solar filters, and we saw sort of the creepy midday. It's sunny overhead, but it's a little bit gray and almost twilight color. It was kind of bizarre. Anyway, it's neat. But having seen the total solar eclipse this year, it's a whole different thing to see an actual total solar eclipse. And if you get a chance to see a total solar eclipse, you want to take it. It's just different. It's just a whole new thing. You get all the partial eclipse stuff, but you get the total solar eclipse. This is a photograph of the eclipse from a few weeks ago. And you see photographs of eclipses, and you see videos of eclipses, and you look up at the sky, and yeah, it looks like that. I mean, it's the sun and with the moon in front of it, so it's not that big, but it's just amazing. It's just up there hanging above you, this little hole in the universe, it looks like, with glowing white around it. I felt like I was one of the characters in a movie looking at extreme special effects, not one of the actors, one of the characters in the movie. Or maybe I was on another world with some bizarre astronomical phenomena going on in the sky. There it is, right above me. So, yeah, that's what the eclipse looked like. There was an XKCD comic before the eclipse where people thought, oh, are all the scientists getting all excited and thinking with the eclipse coming up, they have a lot to do? And I say, from a scientific point of view, it's just sort of one thing going in front of another thing. That's not that big a deal, right? Things go in front of other things. There is science to be done because you can block out the light of the sun, and then you can see things that normally you wouldn't be able to see because the sun wipes them out. One of the classic examples being Eddington back in, I forget exactly which year it was, but Einstein had his theory of general relativity. And among other things, yeah, thank you, Vic, 1919. Among other things, it predicted that starlight would be bent by gravity. Now, if you use Newton's gravity and you're willing to, ignore the fact that you've just divided by 0, you can actually calculate how far light ought to be bent by Newton's gravity. Again, it's not really obvious that you're doing the right thing, but you can come up with a number, but it's a factor of 2 different from what you get in Einstein's general relativity. So during an eclipse, Eddington and another crew went to both Africa and South America to measure positions of stars to pretty high precision around the sun during an eclipse, and it had to be during an eclipse because otherwise they wouldn't be able to see the stars. The sky would be too bright with the sun washing out all of their light. And saw that, yes, in fact, near the sun, the stars were out of position, warped by the sun's gravity just enough to explain what you would expect from Einstein's general relativity. So this was viewed as one of the big confirmations that Einstein's general relativity was a good theory, that in fact we had found something. There was already another thing that was known. We had found something, a prediction that it had made that was different from Newton's gravity. So there is certainly science to be done related to eclipses, and there's also sun science to be done, but it's more a nature appreciation sort of thing, almost more a spiritual thing really than a scientific thing, because yeah, it's, you know, stuff going in front of other stuff. Somebody said sounds like a Monty Python sketch. You know, so we have the ministry of funny walks and the ministry of stuff going in front of other stuff. And, you know, everybody needs a ministry of that. So yeah, so this is the eclipse. This, you know, it sort of looked like that. If you go to Flickr, a lot of the pictures I'm going to show you, I got a Flickr. NASA has a 2017 Flickr photo feed with all kinds of pictures people took of the eclipse, and there's some really good ones there. This is another photo. The difference, of course, here's the previous one, and that's sort of what it looked like in sky. This, you can see, is a higher contrast photo where you can see all kinds of structure inside the corona. And this is part of what's really neat about this. So, of course, the main part of the sun is behind the moon here. You can't even see it. You see a little bit of red here, and I'll talk about that a little later. But all the stuff out here is the corona of the sun. What it is extremely hot plasma that has been flung out from the sun, partly because it's hot, but also because of the magnetic fields of the sun. And all this structure you see where it looks like there's streamers, and then there's, you know, parts that are, you know, it looks like there's ridges and such in there and all that kind of stuff. All of that structure is because of the magnetic field over the surface of the sun. And the magnetic field of the sun is an interesting thing because it's not as stable as the Earth's magnetic field, because the magnetic field weaves through the sun, but then at different depths, the gas in the sun rotates at different rates, and that tends to twist up the magnetic field. And that causes all kinds of fun things. It gives you the solar sunspot cycle. Every so often, the magnetic field gets twisted up, and there's a sudden release of energy as it relaxes to a lower state, and you get a coronal mass ejection or something like that. But one of the other things that happen is you get some of the plasma that gets heated very hot that would normally just kind of merge in and cool back down, you know, cool down to 6,000 degrees like the surface of the sun. But compared to the corona, the surface of the sun is cool. But some of it shoots out up and is channeled along the magnetic fields into the corona, and the corona is in fact at millions of degrees Kelvin. It's really, really hot, but it's also extremely low density. It's very, very, very wispy, and you never see it. Now, of course, you're not supposed to look at the sun anyway because you go blind, but if you have a solar filter, you can look at the sun, or sometimes if there's very thick clouds, but not too thick. So if the clouds are too thick, you don't even see where the sun is. Sometimes if they're thick enough, you can actually look at it and see the ball of the sun. Probably not the greatest idea in the world to do for a long time, but, you know, sometimes you can do that. You never see the corona. The only time you see the corona is when you can block out the overwhelming light of the sun itself. Yeah, and Damien points out you can look at it when it's on the horizon, although even then you don't want to stare for too long. I think it was Galileo, I believe, who even pointed telescopes at the sun when it was on the horizon and wrote about how he always had a flock of blackbirds in his vision thereafter. You know, you can burn out parts of your retina, but with too bright of light. When you block out the main light of the sun, you can see the corona, and that's the only time you can really observe it directly with your eyes. But, of course, you know, there are things called coronagraphs that people use to actually observe the corona at other times. But without that, anyone who wants to study the solar corona needs to wait for an eclipse to happen. Now, of course, there's other things you can see. You may have heard of Bailey's beads. This is a series of pictures taken by the same guy who did the previous thing, going into, I think it's either going into or coming out of the eclipse. I think this one was going into the eclipse. Right, what you see is a series of edges of the moon from left to right. where that bright part is just the last little bit of the sun disappearing behind the moon. And then, so, there's this very bright spot, but then occasionally there's little extra things that you see on the side that have to do with the fact that the moon's edge is not perfectly smooth. But another really interesting thing to me to see in this is you notice, in addition to the very bright sun, there's that reddish pinkish thing that's right on the edge there as well. And you saw some of that in the previous slide, and that's actually what's called the chromosphere of the sun. The sun, we like to think of it as just a big ball of gas that's hot, but it has the atmosphere of the sun has all kinds of different structure and complicated things. And so there's the chromosphere, is a thin atmosphere of gas over what we call the photosphere, is what you usually think of as the surface of the sun, although it's not a hot surface. It's just where most of the light is coming from. But the chromosphere, and some of this chromosphere you're seeing because it's it's pinkish because it's emitting light, what's called hydrogen alpha light. And so when the moon blocks out the main part of the sun, sometimes you can see the chromosphere just barely peeking over the edge. So you see that here in addition to the fading light of the sun as it goes behind the moon. And this, again, this is really what it looked like when I was out there. The eclipse was up there. It was blocked out for about 2 minutes. You see the solar corona overhead. You're just agog looking at this thing. You can't believe that you're seeing what you're seeing. You're just amazed. And then at the right as it ends, and in fact where I was, I'll show you a picture of where I was a little later. There was another guy there who was taking a lot of pictures through his telescope and through a camera, and he had planned ahead a lot, to the point that he had software on the computer that was driving his telescope to take all the pictures so he wouldn't have to watch it during the eclipse. He could watch the eclipse. But it also gave us like a 10-minute warning and a 5-minute warning and a 1 minute and a 30-second warning. It also gave us a 30-second and a 10-second warning just before the thing ended, so we knew when it was about to end. But you're looking at this, a corona overhead. It looks like, it looks like this slide or this, as you're just looking at that. Oops, too far back. It looks like this or this. But then all of a sudden you see this burst of light just kind of come out over the course of less than a second, right on one edge of the moon there. And it's just, it's second. It's a second. It's a burst of light. You see, they call this the diamond ring thing, and then it becomes too bright to look at. But it's just really striking, this corona, and then all of a sudden this burst of light coming out, and you expect to hear the Spake Zarathustra playing or something like that as this light comes out at you. One of the other things is it really looks white to your eye. We always think of the sun as being yellow. And I guess compared to stars like Vega, it is kind of yellowish. But really, the light from the sun is white in that our vision evolved to use the peak of the sun's light. And so what we think of as white is when you are illuminated, much like totally illuminated by the sun. If the sun really was yellow, then white paper would look yellowish under the sun. But right, so fine. Anyway, we think of the sun as looking yellow. It's really hard to look directly at the sun. But this here, when you see this shining of the diamond ring coming out from behind the moon, it's very bright. And yeah, it looks white, as the corona did when you're looking at it. But there's also other interesting things in here that are hard to see. If you look, you'll notice there's little red stuff kind of sticking up, not just the chromosphere, but it looks like there's specific spots that are. And so one of the other cool things that happens during an eclipse is, and this is zooming in on that previous picture, there are what we call prominences sticking out from the surface of the sun. And if you've ever seen 3D renderings of stars, they often have these big loops of gas and these arcs of gas, or even just sometimes, sort of pillars shooting up. And this is a nice one right here. There's some more down here. The people who had telescopes to point at the sun during the eclipse were able to get some really nice images of these. I think I have a nicer one on the next. Yeah, this is a really good image of the prominence that I found. This stuff that you see, it's really there. Now, what's interesting is that the size of this prominence is huge. the Earth would be pretty close, maybe a little bigger, maybe twice the size of my laser dot here, is how big Earth would be in space. So it's, I mean, another way to think about it is the sun in physical space is 100 times as wide as the Earth is. So this prominence is giant. It's also extremely wispy. It's extremely wispy gas that's being blown out from the sun and carried along magnetic fields. Um, uh, the gas is flowing along the magnetic field. Sometimes it comes out of the sun and goes back in. Sometimes it actually comes out of the sun and just keeps going. But you can see these things. Now, sometimes it's possible to see these from the sun even when it's not an eclipse. If you use an H-alpha filter, you will see some prominences on the side of the sun because it filters out all the light except the specific light that hydrogen gas emits at. And while all of the sun glows, the sun's glowing at all wavelengths, so you cut out most of its light, but you keep most of the light from these prominences. So this pink color actually is real. It's because the wavelengths they're emitting at is due to hydrogen. Right, so this, of course, is this prominence, which is the prettiest one. I've seen a number of pictures of exactly this prominence because it was what you saw in the eclipse. But you can see there's others around. So this is, one of the other things. If you have so see, why do we perceive? Yeah, they've seen because it's the hydrogen. There's a transition in hydrogen that emits light right at 6,500 angstroms. Now there is some other light mixed in, but that 6,500 angstrom light is red. And if it's red and then you lighten it or you add some general light, it's going to look pinkish. But if you get a hydrogen vapor tube and in the lab or somehow you get a vapor tube, you shoot electrons through it, it looks pinkish. That's just sort of the color that hydrogen looks to our eyes when it's been excited. And it is just because of a specific transition in the atomic orbital structure of hydrogen that you see when it jumps down. And so, yeah, that's what we're seeing up here on the sun as well. Yeah, hydrogen is pink. Does that mean hydrogen is a girl, or do we not believe in gender roles for atoms anymore? Did we ever believe in gender roles for atoms? I don't think we did. That doesn't sound like a thing. So anyway, this is something that you don't really see this with your eyes when you're looking at the eclipse. You might see just a little bit of reddish around the edge, but for the most part with your eyes, what you see is the corona. If you want to see stuff like this, you can if you use binoculars. Now, I didn't do that this time around, but there were some people near me who had binoculars that were looking to see if they could see the chromosphere and prominences. So that is something you can look for. You have to be careful because if the sun peeks out from behind the moon at the end of the eclipse while you're looking at it with binoculars, you become very sad very fast. So you want to really make sure you don't have unfiltered binoculars pointing at the sun when it's not in total eclipse, because that will burn a hole through the back of your head pretty fast. Yeah, that's kind of interesting. Yeah, you only have a few minutes for totality, so and that was one of the advantages of having this computer this guy had near me, was that it would tell you when you were 10 seconds away, and then you knew to take your binoculars down. You don't want to risk that. That would be bad. Now, so here's the thing. It's kind of remarkable that we get total solar eclipses at all, where you can see the solar corona. It's an accident of geometry that this happens. It's an accident of geometry this happens. Stuff goes in front of stuff, and no matter what, you could see stuff going in front of stuff. We call that a transit often. There's been transits of Venus and Mercury where we look, and if you have a filter where you can look at the sun, you can see the dark spot in front of it. But the eclipse you get where the moon blocks out the sun is because the distance between the Earth and the moon and the distance between the sun and the moon is just right that the moon can just perfectly block out the sun. So that's what I'm trying to show on this diagram here, right? This is supposed to be the Earth, and these are two sight lines. And you'll notice here that the sight line to the edges of the moon match the sight line to the edges of the sun. This picture is very much not to scale. It's pretty much not possible to draw a picture to scale that has the sun and the Earth and the moon with all of them the right sizes and the right distances apart, because the differences in sizes are so huge that you end up with things that are smaller than a pixel. So this is a schematic drawing. This qualitatively tells you what's going on, but it's not quite right. Like this moon, the size of the moon relative to the Earth is not too terribly off, but it should be a lot farther away. The sun should be way, way, way further away and way, way, way bigger. But okay, whatever. The point is that the sun is big and it's far away. The moon is small, at least as planets go, and it's close, at least as planets go, but the ratio of the distance to their diameter is the same almost, and so that the fact that it's the same almost means that if they line themselves up perfectly, one can perfectly block out the other one, and of course that's the moon blocking out the sun because the moon's the one that's closer, so it's the one that's going to go in front of the sun. So it really is, it's lucky in a sense that this happens. You know, all the moon, if the moon was 20% farther away, if it was only half the size, we wouldn't get total solar eclipses. Or if the moon were a lot bigger or a lot closer, we get solar eclipses a lot, but we wouldn't get to see the corona all the way around the same way we do. So it's sort of a nice accident of nature that we have these things that line themselves up so well. Now, of course, if you want to start going all anthropic, you might try and wonder, I was like, oh, why is it? Maybe life needs something like this. And I doubt all that. I suspect it really is just an accident. But it's a cool accident, and so we get to watch it. There are also lunar eclipses. Oh, look, I like my spelling here. Eclipse. Eclipse? I don't know how to pronounce that word. A lunar eclipse is supposed to be a lunar eclipse. So a solar eclipse, when you name an eclipse, you name it after the thing that is, well, no, yeah, you don't even name it right. So a solar eclipse is when the moon goes in front of the sun. A lunar eclipse is when the Earth gets between the moon and the sun. So that's what you're seeing here. This would be, imagine that these are like light rays. And of course, the moon is a lot bigger than the Earth. So, yeah, no typos in Second Life. The moon is a lot bigger than the Earth. Did I say the moon is a lot bigger than the Earth? That was a lie. The Earth is a lot bigger than the moon, and what that means is the Earth has a much bigger shadow that the moon can completely hide in. So the whole moon goes into the shadow, and that means anybody who can see the moon, which is basically half of the Earth. So anybody who lives anywhere on this side of the Earth will have the moon either near the horizon or up overhead in their sky, can see the moon shaded. They can just see the shadow of the Earth falling on the moon, and if the entire shadow of the Earth is on the moon, they see the blood red moon, sort of is what it looks like. But they see the full moon, but darkened out because it's in shadow. Right. In contrast, when the moon on the Earth, it makes a very small shadow. It just makes a little dot, and that's all that you can see. So, and actually, you can kind of simulate this a little bit in Second Life. So if your graphics card is good enough, I'm going to ask you to set your preferences. Go to your graphics preferences and you have to set your graphics quality to the tick between high and ultra. You know, why is the moon red? Okay, so that's a different question. There's no chromosphere there. To be honest, I'm not entirely sure why it looks red. You would expect it to be kind of a very dark gray because it's just there's no light falling out anymore. Vic, do you know why it looks red? So anyway, what I was saying is set your graphics between high and ultra, and then also make sure shadows are set to sun, moon, or at least sun, moon. All right? So if you can do those two settings, yeah, the light going through the Earth's atmosphere will tend to make it redder. That's probably what it is, actually. It might just be that. But the regular moon would have the same problem, so I'm not sure why you notice it so much more when it's dimmer. I mean, some of this may be an eye thing in addition to a light thing. Anyway, once you've got your preferences set, and if you have the shadow set to sun, moon, you should start seeing shadows of the people around and all the objects. The other thing you want to do is under World, you want to click World, you want to find sun position, and you want to check sun to estate time. And if you check sun to estate time, what you should see is the sun should be on the horizon behind me. And you should see nice long shadows, like I have huge leg shadows in front of me. from the sun. If you have the graphics set high enough to have shadows and you have the sun behind me, you'll see that. So yeah, so yes, what you guys are saying, the moon looks redder at sunset for the same reason, or moonset rather, for the same reason the sun looks redder at sunset, is it has to go through a whole lot of atmosphere. Whereas when it's overhead, it doesn't go through nearly as much atmosphere. And the atmosphere preferentially gets rid of the blue light, so the red light gets through better. So yes, the moon will, you know, if you can see it, it'll tend to look redder on the horizon. Although when I lived in Los Angeles back in the early 90s, the full moon was kind of brown always. It was a little gross. All right, so if you have your shadows set right, what I'm going to do is I'm going to move in here a little. Let's see. So did I set the present? Yeah. Well, I have it set for estate time. So I think, but here's the thing: is every client can configure themselves. You have to set yourself for estate time to see this. So what I'm going to do is, first of all, I'm going to move my screen out of the way so it doesn't block the sun. All right, and I'll bring it back down when I need it again. And I've got an Earth here and a moon here. And the other thing you're going to need to do if you want to see this is be able to move your camera around. So I know I'm asking a lot of you here, but and what I'm going to do is move the moon. It's not to scale. This moon is too big. And when I'm done moving it, it's going to be too close to the Earth, but qualitatively, once again, you'll see what I'm talking about. So if you have your shadows set the way I'm hoping you do, so you can see shadows and you've set your sun position to follow what the estate has, right now, back on the stairs, so the stairs of the seat of the first level behind where John 276 is, and in front of where Max is, there's a shadow of the Earth, and then a little off to Max's left, there's a shadow of the moon. And if I move the moon just a little bit, I can actually make the moon's shadow fall on the Earth. Yeah. So now, if you know how to control your camera, here's what you should do is, assuming that everybody's client works like mine and the way all Second Life clients used to work, hold your mouse over the Earth, hold down Alt, hold down the left mouse button and move around, and you should be able to look at the Earth model I have here and orbit around. And if you orbit around to the right side and if everything is set right, you'll see I've got the United States and Central America and South America, and you'll see this shadow of the moon blocking off part of the United States and Mexico and Central America. And this is a simulation of a lunar eclipse, except that the shadow is way too big because I have the moon both too big and too close. In reality, the shadow would just be a little tiny dot, but I've made it bigger so you can see what's going on. But this also says why you don't see a total solar eclipse from everywhere. You just see it from some places. It's because the shadow only falls in some places. In contrast, if I move the moon here to the other side of the Earth, and I do it right, which involves not clicking on the wrong thing, which I just did twice. All right, so I've got the moon now. And if you look, the way I have it right now, you will notice that the bottom half of the moon, a little more than the bottom of the half of the moon, is in shadow, and that's the Earth's shadow falling on the moon. Now, rotate around. Do the same thing where you move your pointer over the moon, hold down Alt, hold down the left mouse button, and move the mouse left and right so you can orbit around. You'll notice, I'm going to move the moon up a little bit. You notice that one side is dark and one side is light. And that's just because of where the sun is falling, right? The sun is coming from behind me, and that is what's making the moon light. So that's where phases of the moon come from. I also have the wrong face of the moon facing Earth, but we will cope. If I move it down a little bit here, you see now the shadow of the Earth is also falling on the bright side of the moon. And if I move it down enough, the moon is now entirely in the Earth's shadow. And this is what a total lunar eclipse would be like. And what that means is anybody who's on the side of the Earth where they can see the moon will see the moon in shadow. So lunar eclipses are more widely available to residents of Earth than solar eclipses are, partly because the Earth's shadow is bigger, so it's easier to get a total lunar eclipse, and partly because anybody who can see it can see it. Now, sometimes you also get a partial lunar eclipse, right? Something like that, and it just depends how things are lined up. So anyway, I'm going to move these guys back here. I will leave them in this orientation if you want to keep looking at the shadow. I'll move them over to here, and I'm going to move my slides back down. Right. So there, there's a little 3D demonstration of light and shadow and all that kind of thing. Right. Solar eclipse, lunar eclipse. This is a picture of a lunar eclipse from 1997, which, speaking of feeling old, I was talking to my students about the discovery of the accelerating universe the other day, and realized that when I showed them a supernova that we discovered in 1997, it was before most of them were born. Anyway, I think of 1997 as being sort of recent. So anyway, 1997, this was a partial lunar eclipse, and you can see this should be a full moon. But this here is the shadow of the Earth. Phases of the moon are not the shadow of the Earth. It's just us looking at the side of the moon that's lit or not. But this really is the shadow of the Earth falling on the full moon. Here's the edge of the shadow of the Earth. You can see that it's not a perfectly sharp edge, and that's because the sun is not a point source. I think the shadows you saw on the models here were actually pretty sharp. I think because Second Life is modeling the sun as a point source infinitely far away. I suspect if I was writing a simple sun model, that's probably how I'd write it. But the real sun isn't quite like that. So you actually get a little fuzziness because the real sun has some size to it. So you'll get a fuzziness at the edge of the shadow and then full shadow in there. So that's what a lunar eclipse would look like. And again, lunar eclipses are not as impressive as solar eclipses, but it's more often that you can see them. So if there's one going on that's coming up, pop outside during the full moon. Take a look at your lunar eclipse. Now, phases of the moon. Many people don't know what causes phases of the moon. I suspect a lot of you do, but not all of you. So here's the sun. It shines light on the Earth. So this is the side of the Earth that's lit by the sun. This is the side of the Earth that's dark. Same thing with the moon. Here's the side of the moon that's lit by the sun. Here's the side of the moon that's dark. And as the moon goes around the sun, sometimes the light side of the moon is pointing away from us. And sometimes the light side of the moon is sort of half and half. So the side of the moon we could see here is half lit, so the moon would look like this. Or if the moon's over here, the side that's lit is facing us, and we don't see any of the side that's dark, so we call that a full moon. Now it turns out the side that we see is always the same side. The same side of the moon always points towards us. So when I say the dark side and the lit side, well, that changes just like on Earth, right? It's not day always in any place, and it's not night always in any place. But there always is at any moment a light side and a dark side. So the whole dark side of the moon thing, yes, there's a dark side of the moon, but it changes over the course of the month, which part of the moon is dark. So when the moon is full, the light side of the moon is the side that's pointing towards Earth. When it's new moon, the light side of the moon is the side that's pointing away from Earth, so we can't see it anymore. But when you look at this, you think, wait a minute, here's the moon. It's between the sun and the Earth. There should be a shadow. And here's the Earth, and when we're talking full moon, here's the sun, here's the Earth, here's the moon. The full moon, we shouldn't be able to see at all. It should be in Earth's shadow. So that begs the question, why don't we have a lunar eclipse and a total solar eclipse every month? And the answer is, things aren't not that well lined up. And also because, I wonder if I could do this to scale. If I tried to do my Earth and Moon thing to scale here, I'm just going to guess, but I'll get it qualitatively right. The moon should be smaller, first of all, and second of all, should be more like way over here and more. And I've now lost it. Oh, in the stands. Boop. There we go. That's more like a scale distance between the Earth and the moon. I didn't measure it exactly, but qualitatively speaking, that's something like what it is. So, right, everything's really far apart compared to how and everything's not perfect. Not just Ptolemy, Copernicus would be disappointed. Well, okay, so here's the deal, is that the moon's orbit is tilted at 5 degrees with respect to the Earth's orbit. So that's what I've tried to draw here, right? Here's the Earth's orbit around the sun. This line points from the Earth to the sun. This line points from the Earth to the moon. There's a 5-degree angle between them. There's actually another angle that is not relevant to this talk, but is important. You'll notice a little line sticking out of the Earth. That's the North Pole. If you actually go to latitude of 90, you'll see there's a big pole sticking out of the Earth there, only it's candy striped, red and white, because Santa Claus painted it that way. Anyway, so that's the North Pole that sticks up. It's the axis that the Earth rotates
Guys,
around.
you see the raccoon?
Hello? Somebody else is talking. And that axis is tilted at 26 degrees with respect to what would be straight up relative to Earth's orbit. And that has effects, like seasons. But that's a whole different ball of wax. So anyway, what's important here is that the moon's orbit, moon makes a circle around the Earth, is tilted relative to the Earth's orbit around the sun. And again, this is not to scale. The moon's orbit should be a lot smaller. The sun should be a lot bigger, etc. But the effect of this is that frequently the shadow of the moon misses the Earth, like the way I've drawn it right here. The shadow of the moon, if you look at the light rays from the sun, it's going to go down here, and sort of where the focused shadow of the moon would fall there, and then more shaded parts fall off here. None of it hits the Earth. So most of the time at new moon, yes, there is a shadow of the moon because, somebody somewhere in a spaceship could be in the shadow of the moon, but the Earth misses it. And likewise, I didn't have a picture for this, but if I drew the moon up here, the shadow of the Earth would completely miss the moon. So most of the time at full moon, the shadow of the Earth, the moon's not in the shadow of the Earth, so we don't see any eclipse. We just see the full moon. And likewise, most of the time at new moon, the moon is, if you could see it in the sky, which you can't really because the sun is so freaking bright, but you would see the moon either north or south of the sun, which if you're facing south and looking, northern hemisphere, if you're facing south at noon, say, and looking at the sun and its new moon, you would describe the moon as being above or below the sun. But again, you can't see it because the lit side's pointing away from us and the sky is bright and the sun is bright. So that's what happens most of the time. And so that's why we don't get eclipses all the time. We only get eclipses when things are lined up just right? Which means, so like here, when the moon happens to be on these parts of the orbit, but then the Earth would have to be over here so that it was lined up just right for the moon to go in front of the Earth. The 5-degree angle will cause some variations in the tides, yes, as well as connecting that with the 26-degree angle. So the details of how the tides happen are affected by all of these things. Intuitively, I wouldn't expect that 5-degree angle to have a really big effect because it's not that big an angle. And tides are a fairly gross effect of gravity from both the sun and the moon. But it'll have some effect. So when the moon orbit around the Earth is lined up just right, that's when you get the shadow. So typically, most years, we only get 2 eclipses of each type, 2 solar eclipses and 2 lunar eclipses. Now, some years, because of just details of how things fall out, there might be more. But most years, there's just 2, and they aren't even always total. So if you look up, I think Vic posted earlier a list of upcoming lunar eclipses, and you can find lists of upcoming solar eclipses. Yeah, there's eclipses every year, but, well, the lunar eclipses, you can see if it happens while it's night. If it's a solar eclipse, it's only going to be visible along a strip along the Earth where the moon's shadow happens to fall. And even then, for most people, it's only a partial solar eclipse, and sometimes it's not total anywhere because the shadow of the moon just isn't lined up quite right for its whole shadow to fall onto the Earth. And so there's always some piece of the sun you can see behind it. So most of the time we get these partial eclipses instead of total eclipses. But when we do get a total eclipse, it's pretty awesome. There's another thing. Somebody mentioned earlier about annular eclipses. So annular means ring-like. This is a picture from China in 2010 of what should have been a total eclipse. So what you're looking at here is the sun blocked by the moon, but you will notice that the moon's not big enough to completely block out the sun. And now you're thinking, well, wait a minute, you told us earlier the moon was just the right size to block out the sun. Well, it is sometimes, but both the Earth's orbit around the sun and the moon's orbit around the Earth are elliptical. They're not perfect circles. And so that means sometimes you're closer to the sun and sometimes you're farther from the sun, or sometimes you're closer to the moon, sometimes farther. It's not a big enough difference that we notice just looking at it. I mean, you hear about supermoons, and people say, oh my, it's going to be a supermoon because the moon is close and it's full. And, you go and you look at it. What do you see? You see the moon. you don't really notice it unless you have something to compare it to. And that's what happens during an annular eclipse, right? So this gives you a sense of how much the difference is. It's like the sun here. It's a little wider than the moon. But that does mean even though the moon is going completely in front of the sun, it doesn't block it out. You can see a ring of the sun all the way around the moon. So this would be a case when either we are a little closer to the sun than usual, or the moon is a little farther from the earth than usual, or a combination of both. Is what's happening here. So you would expect annular eclipses to happen more often in the northern hemisphere winter, because it turns out we are actually closest to the sun, I think, sometime in January. It doesn't vary very much, but it's enough that this near perfect size lineup of the moon and the sun is just right that you get an annular eclipse if you get too close. And what Daly says is exactly right. As long as you can see any of the surface of the sun, you don't want to look at it, because you will go blind. If you have eclipse glasses, though, feel free to look at it. In fact, as somebody was saying earlier, you can look at the sun at any time. Eclipse glasses are poorly named. What they really are is solar filters for your eyes. And it's just the only time people think to look at the sun is when there's an eclipse. But you can look at the sun at any time if you have non-scratched, in good condition, properly made eclipse glasses or solar filters for your eyes. Or, if you're higher end, solar filters for your binoculars or your telescope. So sometimes we get partial eclipses, sometimes we get annular eclipses, and occasionally, when we're really lucky, we get a total eclipse. Of course, eclipses don't just happen on Earth. Eclipses happen absolutely all over the place. And here is the moon Io eclipsing Jupiter. This little thing here is the shadow of Io on Jupiter. So if you lived on Jupiter, you wouldn't survive, because the atmosphere is wrong and the gravity is huge and there's not even a ground to stand on. But if you solved all those problems and you happen to be just in the right place, you would see Io block out the sun, and you would think, hey, that was pretty cool. Saturn casts a shadow not only on its moons if the moons fall back, but at all times, almost, Saturn's casting, I think, yes, at all times, Saturn's casting a shadow on its rings. And you can sometimes just barely see this. If you have an 8-inch telescope or something and you look at Saturn, you can tell that the rings, as they go around behind on one side, you can see that it stops just before the edge of Saturn, or not. So, so Saturn, everything puts shadows on stuff, and that's ultimately what an eclipse is. In fact, stars eclipse each other. There's this thing called eclipsing binary stars, which is one way people discover stars that are binary where you can't directly see the two stars. So in this case, I have a big blue and a little red star orbiting each other. Mostly it's the little red star going around the big blue star in this case, because I'm assuming it's got lower mass. Well, so it comes in. Once the little red star is in front of the big blue star, it blocks out some of the light of the blue star. Now, there is also the light from the red star, but each bit of surface of the red star is not as bright as each bit of surface of the blue star, so it's a net loss in light. So that's what I'm plotting here, brightness, and I've got the various times 1 through 6 labeled with the pictures. When the red star starts to come in front of the blue star, it blocks it out until it's entirely encompassed, and then at number 3 is when the red star is going out from in front of the blue star, and so then out here at 4 you can see both of them again. Then at number 5 the red star starts to go behind the blue star. You get a lossless light, not as much, because the red star doesn't emit as much light as an equivalent area on the surface of the blue star, but you get 2 of these little dips. And so this is what's called an eclipsing binary star, and as Vic mentioned, planets do exactly the same thing. And the vast majority of planets that we have discovered that aren't in the solar system, which is also the vast majority of planets we have discovered, because it numbers in the thousands now. We know thousands of planets outside the solar system were discovered using what's called the transit method. So that's when the planet goes in front of the sun, and the sun's light dims, and depending on the planet, the light of the star only may dim by 1% or less than 1%. And so you have to have pretty sensitive and pretty precise measurements to actually even see this dimming. And things like star spots can make you think you saw something when there wasn't really a planet there. So, this takes some careful work, but we've done a lot of it now from lots of different places. And one of the places that's discovered lots of planets is the satellite Kepler, which I've drawn down here. And Kepler has discovered huge numbers of planets. But yeah, basically what happens is the planet's going around the star. If it's lined up just right, From our point of view, the planet goes in front of the star. If you plot the brightness, you see a dip. And if that dip repeats regularly, then if that peak if that dip repeats regularly, then you know, oh, you're seeing a planet, and you can figure out what its orbit is. So wasn't Jupiter visible during this last eclipse? Yeah, I think it was. You could also see the star Regulus if you were in a region of total eclipse. All right, here's me. This is where you discover that, well, I have a beard and I'm bald just like my avatar. My avatar is quite a bit slimmer than I am. So that's me standing there looking all spastic with my blue shirt. Oh, interestingly, the shirt I'm wearing in that picture is exactly the same as the shirt I'm wearing at home right now. I just heard my wife laugh in the other room. And you can see the kind of nerdy looking eclipse glasses I have on, and I'm looking up at the sky. This guy here is Alejandro Calavaro, I think his name is. So what I did, I just found a spot that I could drive to, and I discovered Princeton, Kentucky. It's right in the middle of where the eclipse is. I drove there. I found a park. I parked. I came out, and I just found whatever other random people were there, and I chatted with them. So there's a mother and some of her daughters here. There's a guy here. There was a 21-year-old kid who had a telescope that he was using, and then there was this guy, and he had his whole setup with his telescope, and this is the one that he had his computer that was talking to us. So this is before the total eclipse. It's during the partial eclipse, and I think this was his nephew, if I remember correctly. And this is all of us looking up at the partial eclipse taken by somebody else. So, documentation that we were really there. Some of the other things you see while this is happening are cool. One of the neat things is that if you can go to where there's a tree that blocks most of the light of the sun, but there's a few little spots where light shines through the leaves, you'll notice all of these leaf spots look like a little crescent moon. What it really is it's the crescent sun blocked out. It's like this one right here is probably the sharpest one. It's what would be the whole sun, but it's blocked out by the moon. And yeah, all you need is a partial eclipse to see this. What you realize is that when there's sort of a bunch of spots of light behind a tree, shining through the leaves, all the little holes in the leaves are acting like pinhole cameras that give you little blurry images of the sun. And during an eclipse, all these blurry images actually turn into little crescents where you see the eclipse. There was one of the guys nearby had one of these mesh hats, straw mesh hats. This is almost right after the total eclipse. He just held it up, and you can see all of the little holes in the plug holes in his mesh hats. You can see all of them are making little pinhole images of the sun. So normally it would just look like a bunch of sort of blurred spots, but here, yeah, you can see all the little pinholes. So, there's lots of cool things you can look for with the partial eclipses. But the total eclipse was just extraordinary. And so as an advertisement, the next time in either the U.S. or Northern Europe, I know that Chantal here is in the Netherlands, which is why I mentioned Northern Europe. The next time there's going to be a total eclipse that goes across the United States is in 2024. You have 7 years, a little less than 7 years to plan for it, so start planning now. What's cool for me is that I live right here. So you'll notice that it's not all that much of a drive for me next time around. I live there, and last time I went to here to see the 2017 eclipse. But here is the eclipse. Here's the 2024 one. I'm probably going to go to there or something like that. In fact, another astronomer and I at Westminster are already talking about trying to have some expedition from our college, because April 6th, school is still April 8th, school is still in session. So if you're in the U.S., think ahead and try to be under the total eclipse, because it's amazing. And the other thing is, don't plan on driving that day. I made that mistake. I thought I was going to drive home from here to here. It's about a 9-hour drive, and I thought, yeah, after the eclipse, it'll be over at 3 or something. I'll drive home. I'll get home at midnight. No. The roads were completely stopped everywhere underneath totality, because so many people had driven in to see it. So just assume you're not going to be able to drive after it, but go for it. I think at this part it's going to be something like 6 p.m. when the eclipse happens. Yeah, traffic was just a nightmare everywhere along totality. So it's coming. Look for it. And if you can find predictions of upcoming eclipses with little lines across the earth of where people will be able to see totality. And so this is the only one in the U.S. in the next several decades. So You don't want to miss it because, you know, you may die before the next one comes, or you'll have to travel if you want to see another one. And it's really, 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 really amazing to see. Um, you know, as I was saying, it was a spiritual experience. I had seen partial solar eclipses a couple times before, where you use pinhole cameras or projection or glasses to see it. But standing down there and looking up and seeing the corona hovering in the sky for those 2 minutes was just, it was eerie. It was otherworldly. All the driving and even the fact that I didn't get back the day I thought I would and had to get a Motel 6 and stay overnight. You know, what should have been an hour's drive away from where I watched the eclipse, but was a lot more than that. It was all worth it. It was worth all the driving I did and everything. And the fact that I wasn't prepared for my classes. When classes start, I just had a better excuse this year. You know, I'm never prepared. Why would you do such a thing? But it was amazing. And I mean, you hear people say this, and it's true. It's all very true. Seeing a total eclipse is just a wholly different experience from seeing a partial eclipse. So I strongly recommend that you find a way to do it. Anyway, that's all I have to say. If there's any residual questions left, I'd be happy to talk about them. And thank you all for coming. Yep. Oh yeah. I mean, yeah. Patio was he was just a remarkable science educator, and public outreach person. Yep. Shades of Micah back in the day. I will try. You know, I haven't given a lot of presentations in the last couple of years. I'm going to try to give at least one or two more this season. Um, Really, if you want me to give more talks, you just have to. Jess has to nag me a whole lot, or Chantal, and eventually, I think that works. But uh, yeah, I mean, there's a few different interesting things I might talk about, like the whole possibility of a 100,000 solar mass black hole, which we call medium sized, near the center of our galaxy would be a cool thing to talk about, or you know, various other things. So, right, well, thank you all for coming. Everyone have a good day, and yes, I will reset the slide to one. Go. All right. Yeah, actually, that's a neat thing. If you can find photos of that online, you can see some photos of the shadow of the moon on the Earth. That's a good thing. Yeah, and as the moon gets further distant, eventually we'll only have annular eclipses and partial eclipses. When? I don't have any intuition for that, but much longer than our lifetimes. So, you know, unless the singularity theorists are all right. All right. Well, thank you all for coming. I'm going to head out, and I'll see y'all later.